So I want to come back to the problem we were talking about when we made the jump to T statistic. At a certain plant, batteries are being produced. A simple random sample of 30 batteries finds a mean life expectancy of 12.35 months with a standard deviation of 2.41. Find a 95% confidence interval for the life expectancy of all batteries being produced. So you can see I filled in the state. Okay, plan. Well, the plan here really doesn't change, even though, we've talked about why we're going to use T. Reminder, our deviation came from the sample. So this is why we're going to use T now instead of Z. And again, remember, the calculations don't change, the conditions don't change. What changes is the amount of variability we allow. And I'll explain that here as we get to the do. So plan, we're making a T interval. We have a simple random sample. We collected 30 bulbs. That's less than or equal to 1/10 all bulbs produced. Or this is not a very good factory if it's not. Now, our sample size is greater than or equal to 30. Remember, that's what we always needed. So I'm just going to make a little note here that central limit theorem, we can say, yeah, it's going to be approximately that normal shape. So even though we're using T, okay, now do. What we're going to do is we're still going to need our point estimate of 12.35 plus or minus. I'm going to leave that spot for the critical value blank. Our standard deviation was 2.41 over the square root of 30. Now you notice really nothing has changed. I'm going to show you the chart. Let's talk about what does change with T statistic. So here's the chart. This is table B. You might want to find your table B and kind of follow along. If you'll recall, degrees of freedom is always one less than the sample size. So our degrees of freedom is 29. So right down here, 29 degrees of freedom. Now I am making a 95% confidence interval. So along the bottom, we're going to find 95% down here. Okay. 95% right down here. So let me do this. So when we were making a Z interval, our critical value was 1.96. But now we use the sample size of 30 to give us 29 degrees of freedom. This is our new critical value, 2.045. So I just want you to think what this is going to do. It's going to widen our interval by just a little bit. The idea being, because we have a sample rather than a population, we need to recognize there could be a larger room for error. So that's what the T statistic does. And again, I just want to re-emphasize, if you have a T statistic with a small sample size, like up here, it's got a very it's got a very wide variability. Down here, with larger samples, it will appear very normal. So from wider to more normal as you gain sample size. And that's why when it says infinite, that really means population size. That's why here we're using a Z star. So this is sometimes referred to as T star. So coming back to this problem, we now have a critical value, 2.045. So again, notice the shape didn't change. The point estimate, of course, is still the point estimate. And the calculation for our deviation for our sample mean didn't change. The only thing that changed was that critical value, because we're saying because we used a sample, we have to allow for a larger margin of error. Let me show you how to do this on the calculator. So you should go to your same stat menu, go to tests, and scroll down to T interval. This is number 8. And you have some choices, data or stats. Make sure you're on stats. Data says you have the whole list of in this case, light bulbs in a list somewhere, and you don't. So I put in my sample mean, my sample deviation, my sample size, and my confidence level, and then hit calculate. So you can see the interval is up here. So I'm going to fill that in, 11.45, 13.25. We are 95% confident that the interval from 11.45 to 12.35 captures the average life expectancy of all batteries produced in the plant. Okay, I want to do one more example, but I want to do it a little bit differently because at this point we've really never dealt with anything that fails this condition. So the question is, what if it does? A swim coach takes a simple random sample of 100-yard freestyle times from his team's past section meet results to find out the average time drop due to taper. These are the time drops. So if negative is good, it means the swimmer went faster. Positive would be bad. It means the swimmer gained time. So construct the 95% confidence interval. So of course we have our state, our plan, our do, and our conclude. All right, our state. Make a 95% confidence interval for the average time drop of all 100 freestyle swimmers who use this taper. Okay, our plan. Well, we had a simple random sample. It doesn't give us any indication of how many swimmers this coach has ever coached, but we do have a sample size of 16. We're going to say, well, I guess I should say all 100 freestyle swimmers. I'm just going to say of 100 free, like this, okay? But our sample size, it isn't bigger than 30. It's only 16. So what do? Well, we have to do a graphical check of the data. We want a graph that shows us if there are any outliers and if there's a lot of skew. The best one to use is a modified box plot. So the first thing you would do is you would go to your stat menu and then edit, and you would put in the 16 pieces of data. And if you wanted to follow along, I can move this so you could see that. And I've already done that. I put my data in list 1, so stat, edit, and then I went to second, y equals, so I get my plot menu. Plot 1 I've turned on. I've chosen to do a modified box plot, so it will show me if there are outliers of my list 1, and then I graph it. Oh, I should mention before graphing, you'd probably want to go to Zoom and then choose number 9, which is Zoom Stat, which fits all of your data, so you don't have anything running off the edges. So there are no outliers. There is some skew, but there are no outliers. Now, I just want to remind you, you should have -1. This is 0. You could write down the values. By using trace, you can find all of the values. You should copy this down onto your paper. When you're doing this on the AP exam, if you have to do a graphical check, you should show them the graph. Okay? Show the grader. And then make a comment about it. There are no outliers. We're going to proceed here. There's a little bit of skew, but nothing that's going to, I think, cause us to stop. But again, make sure on the AP exam, you want to show the grader like, yeah, I actually did do the graphical check. Here's what it looks like. And remember, for a modified box plot, you should have the scale and the plot. Okay, sorry, I got a little messy. All right, let's do this using the calculator. All right, I went to my same menu of stat tests, go to T interval, and this time I changed it from stats to data because I actually had the data in my list 1. And then I told it the level and calculate. So here it is, and you can see it actually calculates the sample mean and sample deviation for you. Yeah. So then let's conclude. So we are 95% confident that the interval from negative 0.967 to negative 0.470 captures the average time drop for all 100 freestyle swimmers using this taper. Again, what I want you to get out of this video, why do we use T instead of Z? It's because we had a sample rather than a population. How are they different? Well, they have the same shape, a lot of the same calculations. T allows for more variability inside our margin of error. The recognition that a sample may have less accuracy than a population. As long as the sample size is 30 or above, the conditions don't change. Here, we may have a small sample, so we may have to do a graphical check. What we're looking for are outliers and a lot of skew. Always on the AP exam, on homework, on tests, write your graph down correctly with a scale on the bottom and the graph above it. Modified box plot is probably the best choice because it's the fastest and gets us all the information we want.